Welcome to the hyperbolic coding chamber. My brain is fried. I just finished like a 9-hour work session. And we still have to do LeetCode. This is torture. The LeetCode devs have conspired to pretty much force us into subservience by completing these problems. This is okay, I'm going to stop, but basically, yeah, my brain is fried. I think I'm going to do the shortest session we've done in a very, very long time. I think we're just going to do 20 minutes. I'll do 25. My brain is absolutely fried. I have returned. Yes, my brain is absolutely fried. But nonetheless, we're going to do our allotted 25 minutes anyway. So, yeah, who knows where we go from here. But that being said, we do have comments as per usual. So I saw this problem. Oh, wait, we have a comment from P Harmony. Guerrilla marketing, maybe. I saw this problem and thought I'd try it out. Didn't realize that duration could be 10 to the 7 and time series could be 10 to the 4. Got a good old TLE. Happens to the best of us. This is truly how it be at TLE. Yeah, TLE is the sign that we're just not good enough. But eventually we will be. And we have a comment from Tree Stars. Yo, fellow Ivan, Jurek, and Joyer, we truly are among us. Yeah, Ivan Jurek is a legend, man. Legendary squat god, squat king. He can crush 30 watermelons between his thighs. So that is where we want to be. So, I mean, we want to be there in terms of programming. So hopefully that will be the case. But yeah, if you guys don't know, Ivan Jurek is a person who squats every day. Pretty epic human being. So hopefully we can reach that level. And also hopefully our philosophical reflections can reach his level of clarity. But all that remains today is to show up to another problem that promises to hurt us. So we're going to do classic 25 minutes. And I think, what was our thing today? We worked on arranging coins yesterday. A problem not really certain why we were able to figure out, but maybe that's just intuition over time. And here we have find all numbers disappeared in an array. So we're just going to see how long we last today. So let's just jump into it. So given an array of nums of you can already tell I can't read. Given an array nums of n integers where nums sub I is in the range 1 to n. Given an array nums of n integers, so n integers long, where num sub I is in the range 1 to n inclusive, return an array of all the integers in the range that do not appear in nums. So looks like we have 1, 2, 3, 4, 5, 6, 7, 8. 8 numbers. So we should have the numbers 1 through 8. We're missing 5 and 6. No, wait. 1, 2, 3, 4, 5, 6, 7, 8. Oh, the way the numbers are missing is by duplicates. Yeah, so we're missing 5 and 6. And then we have 1 and 1, which means we should have 1, 2 inclusive, but alas, we only have 2. Yeah, we're missing the number 2. Could you do it without extra space and in linear time? Makes the return list does not count as extra space. I think what we could just do is create a set and then load all the numbers from 1 to n into the set. And then as soon as we iterate over the numbers again, and if a number using I this time. And if a number doesn't exist, then we'll add it to our answer array. So we'll have an answer array. We'll return answer. Then we'll have our set. And the set is just going to hold a number. Then we'll do for let I equals 1. I is less than or equal to nums. I plus plus. We're going to say set.add nums. Actually, we just want to add the numbers in nums. Nums.length. Then we can duplicate this, and then instead we can count from starting from 1 and going up to and including nums.length. We'll say if the set doesn't have I, then we'll do ans.push I. This looks like it would be linear time, linear space. Follow-up is, could you do it without extra space and in linear time? I think you can do it in linear time. I think we might become Gauss once again. If we sum up all the numbers as they should be, for example, correct sum or actual sum would be equal to nums dot length times nums dot length plus 1 over 2. This would give us the sum of the numbers if all the numbers existed, right? And then what we can do, I think what we can say is while we'll have our answer array still. And I think what we can do is, actually no, we can't do this in linear time. Oh no, wait, maybe we can. Because what I'm thinking is going to be n log n time with constant space. We can't sort because that would mess everything up. Maybe they want us to just modify nums in place. We do it without extra space and in linear time. Without extra space. Without extra space. What if we calculated the entire sum of all the numbers in the array? How do we know in example 2 that 2 is missing? in constant space. The numbers are out of order, so how could you do it with extra space and in linear time? That just don't make no sense. Could you do it without extra space and in linear time? This seems nutty. Could you do it without extra space and in linear time? Is this possible? I feel like you could use the Gauss formula here somewhere, but maybe not. I don't understand. Maybe it's a waste of time, though. Let's just see. Oh, that's really clever. That's really clever. We mark it as negative because we still need to be able to access the indice. We can do that by just using the absolute value. But also, we want a way to reuse the information in that index and be able to tell something, and that is what we use the sign for. That's really clever. That was cool, though. Assume you are an awesome parent and want to give your child some cookies, but you should give each child at most one cookie. Each child, one, has a greed factor, which is the minimum size of a cookie that the child will be content with. And each cookie, J, has a size S sub J. S sub J is greater than or equal to the child's greed. We can assign cookie J to the child, and the child I will be content. Your goal is to maximize the number of content children and output the maximum number. So you have 3 children and each has one has a grade of 1, 2, and 3. The best we can do to optimize this is 1, because only one cookie can satiate one child. Interesting. Maybe we could try a greedy solution. Greedy solution where we pretty much say, actually maybe not a greedy solution first, but I think greedy solution is possible. Idea 2 would be to just I feel like you could sort both data sets in descending order. So 3, 2, 1, 1, 2, 3 would become 3, 2, 1, and then this would become 2 and 1. And then what you can just do is say if and we have 2 pointers for greed and cookie. If greed, right, is less than or equal to cookie, then we increment both. Right, and then we do the same here, both, and then we would just return the number that we output. I think this would work, because even if we have something like this, we have like 5, 5, 5, and we can't satisfy any of these children. If it's greater than, we just if the cookie doesn't satisfy the child, we'll just keep going. Do 5, 5. Right, and then we'll end up doing the same thing. I feel like this does give me a DP vibe, just a slight one, but I don't think it is. So let's try that. And C index is greater than or equal to 0. will return satisfied. And then we'll have some cases if G sub G index is greater than or equal to C sub C index, S, we'll do satisfied plus equal 1, G index plus equal 1, C index plus equal 1. And then if we have a case like we had earlier with the 5, 5, 5, we can still find a less greedy child. So else if G sub G index is less than S sub C index, then we'll just say C index plus equal plus equal 1. And eventually we have to get to the end because this is an else. But there's only 3 cases, and this if statement already covers the first 2. If it's equal to it or if it's greater than to it, it means we found a match. Otherwise we didn't, and we should keep seeing if we can find a less greedy child. Oh my god, it should be minus equal. I trolled. Wait, so we have 3, 2, 1. And 1, 1, we can satisfy this first child because it's greater than I think we have to swap these. This is a little confusing, but G is G is I see. G is the greed factor. And S is the actual sweets you have. So what this should be down here is G index minus equal 1. And if the greed of the child is greater than if the greed of the child is greater than or equal to the sweet of the cookie index, we found a match. Otherwise, it means that the child's greed is less My output is still 2. So we have 3. We'd say, okay. If S sub j is greater than definitely is a blocking issue there. I feel like we can solve this one. I think I just need more brain sauce. So we'll be back tomorrow.